Hey everyone, this is Lalit here again. In this module, we are going to learn to handle datasets, creating, reading from external files, modifying, summarizing, and visualizing in Python with package Numpy, Pandas, and Seaborn. This first video focuses on package Numpy. Through Numpy, we will learn to create and handle arrays. Functions that we'll learn here will serve a major purpose. They will set background for handling columns in our datasets when we eventually move to Pandas data frames. In this particular video, we are going to look at some aspects of Numpy arrays. We'll look at creating ND arrays, or rather 2D arrays, subsetting them with indices and conditions, looking at a few specific comparisons of NumPy and math functions. We'll also be looking at special NumPy functions. Okay. Let's get started with creating two-dimensional arrays. Technically, you can create arrays with more than 2 dimensions, but we don't need them for the purpose of this course or most of the machine learning algorithms, even the ones which are not covered in the course. Okay. First, we'll import the package NumPy, give it alias np. This is a 2D array, and the values that we passed are simply list of lists. So we have passed a list of 4 lists, and each of the individual lists happen to have 3 elements. So that makes B here a two-dimensional array. You can quickly determine size of each dimension by looking at shape attribute of an array. Dimension in NumPy arrays are referred as x's. 2D arrays have 2 x's labeled as 0 and 1. Since there are 2 dimensions here, we will need to pass double indices while accessing them. Counting along both the x's starts with 0. If we want to extract, say, value -1 from the array created here, we will need to access it with its indices across both the axes, which are 2, 0, 1, 2, and 1, 0, 1. For better understanding, we can consider the first index to be index of the list where the element is, so 0, 1, 2, and second to be its index within that list, 0, 1. Indexing and slicing here works just as it worked for list, just in 2 dimensions. Let's look at few more examples. As you can see, this simply gives us second element from all the lists, and this gives us all the elements from the second list. Okay. By default, you can access all the elements of a single list in a 2D array by providing a single index as well. So whenever you pass a single index, by default it gives you output of an entire list. You can pass list of indices as well to access multiple elements of a 2D array. Here elements will come from pairing of indices. So 0, 1, 1, 2, 1, 1, and that gives you 20, 26, 4.5. 0, 1 is this. 1, 2 will be second list, the third value 26. 1, 1 will be the second list and the second element 4.5. You can use this index access for modification also. For example, in here itself, if we wrote this, the elements that we are accessing earlier, if we wrote this equal to some replacement, there are 3 elements, and if we replace them with -10, -20, -30, you will see that in place of 20, 26, and 4.5, we'll end up having -10, -20, and -30. You can subset an array on the basis of a condition also, not just indices. This here is going to return all the elements from the entire array which are positive. Let's say I want to put the condition on a single list, and I want to get all the elements which correspond to those elements in the list. Here I'm going to get elements from all the list, right? This is the index of the list. This is the index of the elements within the list. When I write b2 greater than or equal to 0, this simply gives me this logical list, logical array, true, false, true. When I do this, this logical array will be applied on all the list and corresponding, so here this is true, false, and true. These first and the third values from all the list will come as output. See here? So let's say if you wanted to apply the condition to first element of each list and then wanted to keep all corresponding elements across lists, we will have to write it like this. So this is a logical vector, true, false, true, false. It will have as many elements as there are number of lists. And we can do this. So across the list, it has extracted those values which correspond to logical true and false in this logical array. If we wanted to apply functions which work on multiple values or across a full dimension instead of single value, we will need to use Numpy function instead of math package functions because they work on scalars of single values. Let's try using them anyway. Let's say we wanted to replace the entire 2D list index equal to 1 with its absolute values. Let's try a function from package math. So within package math, there is this function called fabs which calculate the absolute values. And if we write this, I get an error that only length 1 arrays can be converted to Python scalars. Essentially, math package convert its input to scalars, but since b1 here is an array of multiple elements, it fails. Instead of that, we'll have to use the corresponding Numpy function to do this. np.abs, and that works on the entire array, as you can see here. This entire thing after applying the function has become positive. There are multiple such functions available in Numpy. You can write np dot and then hit tab to show you the list of such function. See here, there is all the functions that you could get in math. You will have the corresponding function in Numpy also, which you can use wherever it fits. The advantage here, just to remind you, is that it works on the entire array as well. It doesn't require single inputs. You don't have to write a for loop to apply a function across the array. To better understand the idea of access labels 0 and 1, we will look at functions which collapse the array. For example, np.sum. This sums the entire array. Let's say instead of this, we wanted sum across axis 0. So this sums across the axis 0, which is this here. It doesn't get selected that way, but x is 0, this 21 belongs to all the first element, all the second element 70, 97, all the third element 120. X is 0 here corresponds to elements across the list. X is equal to 1 corresponds to within the list elements. As a note, keep in mind that when we start to work with pandas data frames, which are in a way 2D Numpy arrays, each list will correspond to a column in the data. In that respect, you can say x is equal to 0 represent rows in a data frame and x is equal to 1 represent columns of a data frame. Next, we will look at a small subset of Numpy functions which are commonly used a lot. Rarely used functions in Numpy we'll learn about as and when we come across their specific use cases. These functions help in quickly creating special kind of Numpy arrays, starting with Numpy or np.arrange. This gives you an array which goes from 0 until 6 minus 1. That is 5. You can use starting and you can control starting and ending of an array As you can see, arange function can be used to create sequence of integers with different starting and ending point having increment of 1. For creating a more custom sequence, we can use function linspace. Here, argument num essentially represents number of elements in sequence. Elements in sequence are naturally equally spaced. You can also create new arrays by randomly sampling an original array or simply creating an array with random numbers using random package within Numpy. This creates a random array of size 2, 3 having random integers between 10 and 1. Simple random function within the package random creates an array of given size. So here the size is 3, 4. The random numbers being created here are real numbers between 0 to 1. There is another wonderful function choice in package random of Numpy. So here x is a simple array goes from 0 to 9. This here will select 6 random numbers from this input array. Every time you run this result will be different. You can see here that it is ending up sometimes picking the same elements again. If you want to avoid that, if you want to do sampling without replacement, you need to set replace equal to false, which is set to true by default. Okay. Now, every time you run this, you will get different results, yes, but you will never see one element being repeated here. We will be using random.choice function to simulate data a lot many times in coming module. This here ends up picking A or B randomly 6 times. Let's increase this number. If we look at unique values which y takes, that's naturally going to be A and B. By default, here both A and B get picked with almost equal probability in the random sample. Although this doesn't mean that individual values are not random, but overall percentage of A and B remains almost same. We can force approx probability structure by using option P in random.choice. You can see here now value A appears approximately 80% of the time. Value B appears approximately 20% of the time. Keep in mind that individual values are still random in Y, just that overall A will appear 80% of the time as specified here, B will appear 20% of the time. Another thing to keep note is that these probabilities are not going to exactly match because the underlying process is inherently random. So it will be close to 80 and 20 the structure, but it might not match exactly 80 and 20. In fact, if you're drawing samples of smaller size, the difference might be pretty wild. Let me show you. Let's say I'm only drawing 10 items there. I'm trying to enforce the structure 80-20. It doesn't match at all. It ended up picking all the values as A. Let's try it again. So sometimes it matches, sometimes it doesn't. This match will be more close as you draw more or larger samples from the data. Another useful function is sorting the array. So to look at that, let's quickly create an array. This is an array containing integers from 12 to 100, and there are 15 integers in this. X.sort will sort the entire array. Sorting happens in place, so it doesn't return anything. X itself is now sorted. Now let's look at 2D arrays where sorting will be more interesting or confusing. This is a 2D array, again contains values from 12 to 100, is of size 4 to 6. If I simply sort, the correspondence between the elements is broken. you can see here each individual list is sorted from smallest to largest, but the correspondence is broken. These 63, 68, 40, 42, these elements belong together, but now there are no correspondence coming from the previous structure. This is not what you will generally do. So in case of 2D arrays, what you can make use of is argsort in a clever way. For maintaining order along either of the axes, what we can do is that we can extract indices of the sorted values and reorder original array with. These are third elements of all arrays. Let's say I want to sort my 2D array by these, and other values should move with them, maintaining correspondence. If I use function argsort, instead of sorted values, it tells you indices of the values which should appear in this order for this array to be sorted. Meaning the value with index 3, which is 42, should appear first, then the value with the index 2, which is 51, then 59, and then 77. I can pass these indices now to arrange all my lists according to that here. So the first part is nothing but if I had manually written 3, 2, 1, 0. So my lists are going to be rearranged in that order. So I have now rearranged my list. The last guy has gone to the first and the second and so on. All the lists have been arranged by this order across the third index or third element across the list. You can see that the correspondence doesn't break here. Similar to sort and argsort, another useful combination at times is max and argmax, and its counterparts min and argmin. X.max will simply give you the maximum value. X.argmax, however, will give you argument or the index of the maximum value. So this 95 lies at the index 7. We'll stop our discussion on NumPy here. Other NumPy related functions which are not as often used will be discussed as and when we come across their use cases. In the next video, we'll start with pandas, the go-to package for handling datasets in Python. See you in the next video.